Um, all right. So hello everyone. I'm Hun Lam from Department of Physics, Kansas State University. Today in this presentation, I would like to discuss the possibility of producing Condor gas phase molecules for future experiments at the James McDonald Laboratory, or you can call it JIML for short. So during the presentation, we will be looking for the answers for several questions. For example, why do we need Condor molecules and how can it improve the experiment at JIML? And if we actually need them, then how can we produce them? I will propose two solutions to do so. And finally, based on our criteria, we will discuss which methods should we choose to implement. So first of all, why do we need Condor molecules and how can Condor molecules can improve the experiments at JIML? Right. So the first reason is that Condor molecules will significantly simplify the spectra and the interpretation of the experiment. So on the figure on the left, you can see the simulated absorption spectrum of CS3NO2 at different temperatures. From room temperature down to about 8 Kelvin. Um, and at low temperature, like 8 Kelvin, the absorption spectrum only has two dominant frequencies, which means you only have two transitions involved in the experiment. However, as the temperature increases, there will be more and more transition um, happen in the spectrum, and it will be more difficult to figure out what's going on in the experiment. Like we cannot understand the experiment anymore. So a lower temperature will give us a better advantage of understand the experiment, like what's going on. The second reason is that core molecules will enable the possibility to study some new physical phenomena. Um, Here's the list of some phenomena that associated with different temperature. And this is the log scale, so which means when you go up one square on this ladder, the temperature increases by a factor of 10. And you can see, like for example, if you want to study the vibration and the rotation of the molecules, it's very difficult to study them at room temperature, and you have to cool the molecules down to about 1 Kelvin or a few Kelvin to study those motion. And what is the current status of JIML on this scale? So many experiments at JIML were performed at a temperature of about 100 Kelvin. And it is achieved by using a gas jet design called effusive gas jet. And is it possible to reduce the temperature in this experiment by using another design of the gas jet? For example, Sin and co-workers use a design they call cryogenic buffer gas, and they was able to cool the molecules down to about 5 Kelvin. Another design is called Supersonic Expansion, and it was able to cool the molecules to less than a Kelvin. So I will discuss the two solutions in details, and then we will compare them. In supersonic expansion, we will create a fast flow of cold molecules. So as described in this schematic, we will start with warm molecules in random motion in the reservoir. Okay? And when the molecules reach the nozzle here, if the diameter of the nozzle is much larger than the mean free part of the molecules, then during the expansion, these molecules will collide with each other. And during the collisions will convert the initial thermal energy of the gas into the forward kinetic energy. And when they don't collide with each other anymore in this zone of silence, the molecules will reach their lowest temperature, and we have a very fast flow of cold molecules. So if you are familiar with physics, you will know that the random motion of molecules, we call it the thermal motion, and this is closely related to temperature. However, the mean velocity in this directional velocity is not related to temperature. Right? And when we on up, the initial thermal energy will be converted into directional velocity. So the gas beam will move very fast and faster than the speed of sound, and that's why we call them supersonic expansions. And in this table, you can see that the we can cool several noble gases down to below 1 Kelvin by using the supersonic expansion. The second solution is the cryogenic buffer gas. The idea of this method is that instead of directly cool down the molecules that we are interested in, we will cool another gas we call the buffer gas. For example, in this case, this would be helium. We can cool it down using a cryo cooler to about 3.4 Kelvin, because helium is easier to cool down than other gases, and it's also exists in gas phase at low temperature. Right? After that, we will introduce the molecules of our interest through the capillary here, and when these molecules interact with the helium, they will transfer heat between them, right? And then the warm molecules and the cold helium flow will reach a balanced temperature. So Singh and co-worker used the laser to measure the spectrum of the molecules, and by comparing the absorption spectrum of the molecules with the uh, simulation from theory, they concluded that the temperature of the molecules, which is ammonia in this case, is about 5 Kelvin, which means it reached a fairly good thermalization with the 3.4 Kelvin helium. So if we consider our first criterion about what's the temperature, then we see that supersonic expansion produces the condensed molecules. And as I mentioned earlier, the temperature of the molecules is closely related to the velocity distribution. And the narrower the velocity distribution, the colder the molecules. So in this figure here, you will see that supersonic has the narrowest velocity distribution. So it produces the condensed molecules. And is it colder than buffer gas? And buffer gas will be colder than effusive gas jet. However, there's another thing that we need to take into consider is how actually the about the density of the gas, right? Or you can call it the intensity of the beam, gas beam. Because if you don't have enough molecules in the gas beam, then it will be very difficult to do the experiment. If you have more molecules in the gas beam, it will be easier to do the experiment because you have more statistics. And so this table shows the intensity of the gas beam by using different methods, and we can see not always but typically the buffer gas method will produce the highest intensity. Is higher than the effusive gas jet, and the supersonic one will have the lowest intensity, which is lower than the effusive gas jet. So in summary, I proposed two solutions to produce corner molecules to enhance the experiments at JIML, which are supersonic expansion and the cryogenic buffer gas cooling. And by having these corner molecules, we can gain significant resolution in the experiment, and it's also possible to study some new physical phenomena. And if the temperature is of the most importance, I recommend using the supersonic expansion. And if the density, gas density is of the most importance, then I recommend using the cryogenic buffer gas cooling. And okay, thank you for your attention, and I'll take any questions that you have.
Can you go back to the cryogenic buffer one? Is that what this graph is right here?
This one,
Oh no, the next slide. Sorry.
this one.
Can you explain to me the difference between the supersonic and effusive again?
Oh, so the effusive gas jet is the design that currently used in JIM, and the different is so in supersonic gas here. So you reach a condition. So by controlling the pressure in and the diameter of the nozzle, you will reach a condition in that. In the expansion, there will be many collision happen, and those collision will convert the thermal energy of the gas into the directional motion, which is not related to temperature. So in effusive gas, their design is that there will be no collisions happen when the gas go into the vacuum. So there will be basically no cooling happen there, and, and the gas will be much hotter in that case.
Okay, that makes a lot more sense then. Okay, I think I must have missed that.
Sorry, what?
Sorry, I must have missed that or one of the little bit apart. It makes a lot more sense now.
Okay. Ahmed, you have any question
Nah,
about?
I'm good. Don't have any question.
Right. So I think one question that probably you guys might think about, like how can we get these like very low temperature but still in gas phase, right? Because let's say normally like you have water, you have liquid phase in the normal room temperature, and then you have solid phase basically after below 0 degree, which is about 300 Kelvin already. So these guys are possible that to produce the gas phase at very really low temperature like this is because actually the phase transition depends on both the temperature and the pressure, right? So if you make the gas dilute enough, which means like they are well separated from each other, like the gas like one molecules is far away from each other and they don't interact with each other, then they won't stick together. So basically the density of the gas is low, then it will be possible that to you produce like really cold molecules at really low temperature. All right, so if you guys don't have any other question, I think I will stop the recording here.